SwayamPrabha. Digital India. Educated India.
Good morning, gentlemen. Let's continue our discussion of development of higher order elements so that we get a faster convergent result. So if you are, last class we have seen that if you are looking for pth degree polynomial, we are looking at higher order approximations. So we are looking at 1D for the moment, wherein we are using polynomial of pth degree polynomial, which we equivalently put as n151 up to so there are is a pth degree polynomial and put equivalent to p plus 1 nodes. One, two, three. So there are p plus 1 nodes, and then we are fitting a pth degree polynomial, and these two are equivalent, and then we have seen how the shape functions can be obtained by invoking phi is equal to phi1 at x is equal to x1, and like that phi is equal to phi2 at x is equal to x2. So like that we have seen a detailed mathematical procedure how to get the shape functions. On the other hand, so we can directly get shape functions. And nice. So how do we get the shape function corresponding to different nodes here? So we invoke the property that these shape functions have to be equal to a value of 1 and 0 at other nodes. So for example here, that ni x is equal to 1 at node I and equal to 0 at all other nodes. So if you want to invoke this one, so obviously say at node 3 if you have to have a value of 1 and 0 like this. So for n3, so n3 has a value of 1 at node 3 and 0 at all other p plus 1. So obviously if you want to generate a polynomial function which satisfies this property, so it will be a pth degree polynomial obviously. So it's a pth degree polynomial and so because of these special properties, so these properties are quite similar to the Lagrangian polynomial. So what is Lagrangian polynomial? So it is, say if it's a paired degree polynomial, it will have p plus 1 polynomials and corresponding to I. So it has a p plus 1, either we call it nodes here or here they call it as station points. So it has p plus 1 station point, and so it will have this form. So it is x minus x1, x minus x2, and x minus xi minus 1, x minus I plus 1. So I is missing here. And xp minus x1, sorry, xi like this. Okay, so if this is a very simple polynomial expression, so where you can see here that this will take a value of 1 at x is equal to xi and 0 at all other x is equal to xj, let us say j not equal to I. Okay, you can see that when x is equal to xi, the numerator is equal to denominator and it's equal to 1. And when x takes any other value, okay, so like x2 for example, so the numerator will be 0 and this whole function will be 0. So this is also is illustrated here. This is for n3 here. Well, this is the representation for Lagrangian polynomial. So it's a paired degree polynomial corresponding to the ith station point or ith node here. So here, so that means that our Nix is nothing but Vx. Okay, so thus the shape functions are simply equal to the Lagrangian polynomial. So this is a very simple way of constructing the shape functions for 1D case, and we can write it down clearly. So let us just go back to, say, 3-noded quadratic element as with 3 nodes. So if you want to construct it using 3 nodes, a quadratic element, so this is phi hat x is simply a0 plus a1x, a2x square, and equivalently we can write it as n1 phi 1, n2 phi 2, n3 phi 3, right? And where n1 is simply lambda 1 of quadratic, that superscript not square, it's actually the representation of the polynomial order, and this is equal to, now you can see here, it's x minus x2, x minus x3, x1 minus x2. Okay, so this is n1, right? You can very clearly see when x is equal to x1, this is 1, and at x2 and x3, it is 0. So similarly, we can also write n2 as x minus x1, x minus x3, so you can see this is a very simple and easy procedure. Okay, so this is for 3-noded quadratic element, and this is how we can develop it. On the other hand, we can even, instead of writing in simple natural coordinates, so where we'll write it in terms of xi, right? And these are 3 nodes. So it goes from -1 to +1. Xi goes from -1 to +1. And the middle one is, of course, 0. And so that way we can write the same thing in terms of xi. So it's minus xi, 1 minus xi by 2. You can, so it is nothing but coming. So you can see that when xi is equal to -1, so this is 2. Exactly the same procedure. This is, you have to put it, say, in the form of xi, for example, xi minus 0 here, and xi minus 1 here. And here you put it as -1, and this is -1, -1. So you can simplify it like this. And they will become so these are the 3 shape functions in terms of xi, right? You can see very well, even the n3, when it is +1, it is equal to 1, and at -1 and at 0, so this is 0. In fact, this is the natural coordinate, so the correspondence between these two coordinate system, the actual coordinate system is x, and this is a simplified expression in terms of natural coordinates. So here, so the transformation between these two is x bar is x, and xi okay, so this is the transformation between x and xi, and so xi, if you want to get it from x, so it's x minus x bar is half of it, and divided by h is x3 minus x1, and this is how you get it. This is actually 2h. Okay. Okay, that's by 2 is there, so just make that correction. So this is how the 3-noded element, quadratic element, can be developed, and this is the in terms of xi, and this is in terms of. So as an example, if you want to derive a one-dimensional solid mechanics here, axial rod problem, solid mechanics. This is a one-dimensional thing. So this is a thing, and then you can write it in one dimension. So you can write for one element ijk here. So this is a three-noded element, or one element with three nodes. Say ijk. Right? So here we use the variational approach where, of course, here the transformation here is that x bar is xk minus xi by 2 and h is xk minus xi by 2 and x is equal to x bar plus xi h, and these things are given like this one. Okay, and the shape functions are ni is minus j 1 minus j square. So just for the sake of completeness, I am repeating it here. Okay, so this is a complete description of the transformation between xi and x. And what is that? If you recall, the stiffness matrix will be of the element. What is that? It's a B transpose, and here we write it E remember? So this is the B transpose, E times P, A is the cross section and dx is the variable. So here B is not constant, so you cannot take them out, so it has to be inside. What is B? So B is the strain displacement relationship. Relationship in the sense that if U here is given as N1, U1, write it in terms of J. Okay, so this is for U, and epsilon here is of course only one quantity here, is dni by dx, dnj by dx, so this is the matrix B here. So this is the matrix B here, right? So what is B? B is nothing but dni by dx and dnj by dx and dnk by dx here. Okay, so either you write it in terms of 1, 2, 3 or ijk, they are all same. So dni by, so what is ni? Ni is minus xi plus xi square by 2 1 minus xi square So what is dni by dx? Dni by dx is nothing but, here it is very simple. It's a very simple transformation. So we can write dni by dz, dz by dx. Otherwise, we may have to use the Jacobians and other kind of transformations rules. So dni by dz, here it is minus 1 plus 2 xi by 2. That's what it is here. And dz by dx here is how much? So xi, if you take it derivative with x, so it is 1 by h. H is the size of the thing. So similarly, we have dmj by dx. It's 1 minus xi square, so which is equal to minus 2 xi by 2, and the same thing 1 by h. dnk by dx, and this is 1 plus 2 xi times 1 by h. So these are the derivatives of ni, nj, and k with respect to x, and then we will have to put it in this one and do the integration. Okay, so the k matrix here of the element is nothing but the integration xi to xk so okay times e so this is b transpose e times this one times area is also there. Area is, you can put it here or here, times dx, and dx is how much? It is h d xi. So if you want, I can put it right here. And if it is d xi, then this limits, I'll change it to -1 to +1. So this can be integrated. For example, if you want k11, it is nothing but 1 by h square and a here times -0.5 plus xi -0.5 plus xi. Okay, so this is seven by 6. Okay, so this becomes 7 by 6. So this is for k11. So similarly, you calculate all the other terms. Similarly, other terms like kij is nothing but bi so in a nutshell, I put it like this. So the full k Okay, so this is the K matrix. So here you have to remember that here we need integrations to be done here. These are not, B is not constant. In fact, this is not a constant strain element anymore with the 3 nodes of 1 dimension. Whereas for linear element with 2 nodes, it was a constant strain. So this is for K. And apart from this, so if you want to find out the nodal loads of the element, so this is nothing but N transpose Q dx. Okay. So this is nothing but -1 to +1 N here minus xi 1 minus xi by 2 1 minus xi square times q h d xi. Okay, so those integrations will come out to be like this. So each one of them has to be integrated. Q is the load which is there here, assuming that it is constant for the element. You can put it, and dx is now h d xi, right? And so the integrations are not simply 1, 1, 1, so it is 1, 4, 1, and accordingly you can do that. So this is for one element, and then you can do it for other elements as well, and then you can do the same procedure. In fact, this is for 3-noded quadratic element. You can also do it for 4-noded cubic element, where the nodes will be 4 nodes equispaced. So it's -1, -2 by 3, -1, -1 by 3, +1 by 3, and +1. So like this, so you can have 4 nodes and exactly develop the same procedure. Find out the u like this one, express it in terms of nodal values, including another node here, and then the derivatives will be like this only, but with one more term. So like this, the procedure is same. Maybe the integrations will be a little bit more involved, but exactly you'll get the terms in the same procedural form. So we'll stop it here, and we'll continue our higher order element development in our next class. So that's for 2D. Okay, for 2-dimensional higher order elements, we'll take it up in our next lecture. So bye for the moment.